All right, we're just looking at a quick video on angular momentum in orbits. So if we look at an elliptical orbit here where we have a planet orbiting around a sun, we're going to define our parameters here. Is we have the velocity of, let's get some color here, velocity at position B, and it's an orbital distance equal to r sub b from the sun. And then as it moves around, it'll be going a little bit faster. That'll be the velocity of A, and again, an orbital distance of r sub A as shown in the diagram. So there are two ways that you could figure out if you know information about most of the objects. If you know information about the velocity, the distance, and this distance, and you say you needed to solve for that speed, you could certainly use conservation of energy, but that would be very challenging because you would set the mechanical energy at position A equal to the mechanical energy at position B. You have a lot of alphabet soup going on there. You could do it, but it's definitely more challenging than you would want to. Angular momentum is much easier because the equation is much simpler. It's one term. Angular momentum is conserved. So the reason why we can tell angular momentum is conserved, if I look at just the planet system, the only external force acting on it is the force of gravity, and the force of gravity will not exert a torque because that force of gravity, which acts along this radial line, passes right through the axis of rotation, so it would exert no torque. In fact, if we looked at the planet-star system, angular momentum would still be conserved, but in this case there would be no external forces at all. They would all be internal, so it would be conserved for that reason as well. Just as a quick review, because I always like to throw this in, if I was looking at if I was looking at conservation of mechanical energy, if I looked at just the planet system, this would just be looking at the kinetic energy, which would define the mechanical energy, and it would be not conserved, because you have that external force, the force of gravity, which is causing the satellite to speed up and slow down. If I looked at the planet-sun system, then that would include kinetic plus gravitational potential energy, and yes, it would be conserved. So just kind of a little review on system identification and conservation laws. All right, we'll hop back to our momentum discussion. Angular momentum discussion. I'll talk about this cautionary tale in a moment, but essentially if I look at position B and compare it to position A, the angular momentum at position B must equal the angular momentum at position A, for the reasons we stated. So angular momentum will treat these planets as particles. So the angular momentum of a particle is simply the radial distance it lies away from the axis of rotation times the mass times the velocity at that location. I guess we're putting B over here. I'll make that B. So remember, RMV, or Registry of Motor Vehicles, easy way to remember it, and that has to be equal to the radial distance for particle when the planet is at position A times the velocity at A. So masses cancel out and you get a simple ratio. If I take the ratio of the two orbital distances, that will be inversely proportional to those velocities at those points. So the further away it is, the slower the speed. So that's an easy way to calculate speed when you're given an elliptical orbit and you know things about orbital distances and one of the speeds. So just a quick review about where that RMV came from, in case you forgot. So angular momentum, as written on your equation sheet, is I times omega. We treat these as particles, so this is mr squared. And we replace angular velocity with v divided by r. And that simplifies to the Registry of Motor Vehicles again, so in case you forgot how that works. All right, my cautionary tale is about position C. So the angular momentum at position C is the same. It is conserved. However, the angular momentum at position C would involve a sine term because it is not perpendicular to the force of gravity here, or to the momentum vector is not perpendicular to the r value here. It is at an angle, so there would be an extra sine term, and you would need to be given some information about the angle there. Right, so that's just your cautionary tale. And then I just put together a simple ratio problem just as a practice. So if this distance is 6 billion meters from the sun, and the velocity, comet's velocity, is 12,000 meters per second, and this distance, big D, let's say this is the comet speed at aphelion, 6 is 24 billion. So this would be kind of the standard, and I need to find what is the velocity at this position. So that would be my question mark, and I would just simply set up a ratio. So we'll call this position B and this position A, and that would be 6 billion is to 24 billion as, let's see, velocity at position unknown is equal to the velocity here. So again, that inverse relationship, and you can solve for that speed. So that's just your extension question.